So you want to make a lithium-ion battery. Good timing. Scrib's little robot already has the computer chip we made from a quartz rock. The brain is installed, the switch is on, and absolutely nothing is happening. Apparently, intelligence still requires electricity. We need something small enough to carry, powerful enough to run the machine, and rechargeable enough that we don't have to build a new one every afternoon. We need a battery. More precisely, we'll make one lithium-ion cell, then combine several cells with protection and cooling to create a battery pack. And no, we're not building this at Scrib's workbench. Real cells require controlled factories. Opening, crushing, heating, or shorting one can be extremely dangerous. Our cell uses two materials that hold lithium differently. The positive electrode uses a lithium metal oxide called NMC. The negative electrode uses layered carbon called graphite. Add aluminum foil, copper foil, a porous separator, liquid electrolyte, and a metal case. The trick is arranging them so ions and electrons take different routes. We'll come back to that. First, we have to build the layers. The positive side begins as NMC powder. It is mixed with conductive material and binder to produce a carefully controlled coating mixture. A machine spreads that mixture across both sides of a long sheet of aluminum foil. The aluminum is a current collector. It gives electrons a low-resistance path to the terminal, but it is not the main material storing the energy. On a second production line, graphite-based material is coated onto copper foil. Copper becomes the current collector for the negative electrode. Scrib suggests pouring both powders into the metal can and shaking it. The factory has declined his proposal. Instead, both coated foils are dried. Heavy rollers then compress the coatings to a controlled thickness and density. The particles need good contact without blocking ion movement. The wide rolls are cut into long, precise strips. We now have one positive strip, one negative strip, and a thin, porous separator that must always stay between them. The separator looks unimpressive but has an essential job. It prevents the electrodes from touching and creating an internal short circuit. Its tiny electrolyte-filled pores still allow lithium ions through. Electrons are not supposed to cross it. Remember that. The entire battery depends on electrons being denied the convenient shortcut. Now stack the positive electrode, separator, negative electrode, and separator into one long layered sandwich. Attach metal tabs to the current collectors, then wind the entire stack into a tight cylinder. This is the jelly roll. It isn't dessert, although it does contain more stored energy than Scrib's lunch. Insulation keeps exposed edges and tabs from shorting against the case. Then the jelly roll enters a cylindrical steel can. Next comes the electrolyte. It is added under very dry, carefully controlled conditions and works its way into the pores of both electrodes and the separator. Even small amounts of moisture can react with cell materials and damage performance, so Scrib's drink has been removed from the building. The cap, terminal, electrical insulation, and pressure relief features are assembled. The cell is sealed. It looks finished. It is not. A newly assembled cell must go through formation, its first carefully controlled charging and discharging steps. The first charge moves lithium from the positive material toward the graphite. At the graphite surface, some electrolyte reacts and forms a protective layer called the solid electrolyte interface, or SEI. A useful SEI limits further electrolyte decomposition while allowing lithium ions to pass. Its quality affects resistance, lifetime, and safety. So the cell spends its first hours moving slowly through the factory's tutorial level. It is formed, rested, measured, and tested before anyone trusts it. Now we have a finished cell. But before it goes into the robot, we need to understand what the factory has actually built. Imagine unrolling the jelly roll and magnifying one tiny section. There is NMC coating on aluminum, an electrolyte-soaked separator, and graphite coating on copper. Winding the sandwich fits a huge active surface inside one small cylinder. The active materials hold lithium, the electrolyte carries ions, the separator keeps the electrodes apart, and the metal collectors connect them to the outside circuit. Let's make it do something. Start with a charged cell. Much of the mobile lithium is stored between layers in the graphite negative electrode. Connect the cell to the robot's motor, and two movements begin at the same time. Inside, Lithium leaves the graphite as positively charged ions. They travel through the electrolyte and separator pores into the positive material. Electrons cannot follow through the separator. Their useful route runs through the copper collector, out through the robot, and back through the positive terminal. As the electrons travel through the motor, they deliver energy. The motor turns. Scrib finally gets a reaction from the machine, although the first reaction is driving directly into a wall. Ions and electrons reach the same side by different routes. If electrons crossed inside, they would bypass the robot and produce a short circuit instead of useful power. So where did the energy come from? The electrodes do not hold lithium at the same chemical potential. During discharge, the cell moves toward a lower energy arrangement. The voltage reflects that difference, while the external circuit lets electrons do useful work. The battery is not a warehouse full of electricity. It moves between a higher energy charge state and a lower energy discharge state. To charge it, connect an external power source. The charger pushes electrons back toward the graphite through the outside circuit. At the same time, lithium ions leave the positive material and travel back through the electrolyte toward the graphite. The lithium returns between the graphite layers. Outside energy has pushed the system uphill, restoring the charged state. So charging is not refilling an electron bucket. It is rebuilding a chemical separation. This process is reversible, but it is never perfect. The cell has internal resistance, and moving current produces heat. Heat losses rise strongly as current increases, which is why demanding high power from the same small cell makes thermal management increasingly important. The cell also ages. Interface layers can grow and consume mobile lithium, resistance can rise, and internal materials slowly degrade. During unfavorable fast charging, especially when cold or nearly full, lithium may plate as metal on the graphite instead of entering its layers. That reduces performance and can create safety problems. Contamination, damage, overheating, or separator failure can create an internal short circuit. The rapid heating can trigger further heat-releasing reactions, and in severe cases, thermal runaway. That is why a real battery needs more than cells. Test every cell, then arrange them into a module. In a series chain, each cell's voltage adds to the next. Parallel groups retain the cell voltage while sharing current and adding capacity. Real packs often combine both arrangements. Add holders, bus bars, protective elements, temperature sensors, cooling, and a battery management system, or BMS. The BMS monitors voltage and temperature, estimates the pack's condition, balances cells, and limits unsafe operation. It cannot repair damage, but it can stop one problem becoming much larger. Cooling reduces hotspots. The enclosure protects everything from vibration, impact, and the environment. Combine the test in cells, connections, cooling, sensors, BMS, and protective case. Battery pack acquired. Scrib installs it beside the computer chip and switches on the robot. The sensors wake up. The motor controller responds. The robot rolls forward and stops. Right. It has a brain and an energy source, but no proper muscles. We started with powders, foils, and a thin plastic separator. By arranging them into controlled layers, we created two coordinated pathways. Ions moving inside the cell and electrons doing useful work outside it. The battery is complete. Next, Scrib may need an electric motor.